Hello, I am Nobuyuki Kanaya from NICT Japan. I will give a presentation with the title NEMIANA Cross-Platform Execution Migration for Debugging. Here is the outline of the presentation. First, I will introduce the background and explain the goal of this research, the use case of NEMIANA, and the contributions. Next, I will describe the key idea behind NEMIANA and show the system architecture and its prototype system. After that, I will present 3 case studies. Here is our research background. When developing software for IoT or embedded devices, developers often use different platforms for debugging the software. And the different developing platforms have CPUs from the same instruction set. For example, ARM Cortex M3 and RISC-V RV32i are in the same instruction set of architecture. The first things I would like to emphasize is that CPUs and peripheral circuits are integrated in a single FPGA chip such as Xilinx Ultrascale, and such FPGA boards are often used as debugging platforms. The second one is that the developer chooses a suitable debugging platform for each development phase. For example, programmers run software emulations such as QEMU to debug or test program. This is because in some projects that a circuit board and its software are developed in parallel, and the circuit board might be not available in the early development phase. Once a target board is available, both debugging using the board and software emulation are conducted. Our goal is to provide a debugging tool that makes debugging easier across various debugging platforms efficiently. NEMIANA has the following 2 functions for efficient debugging. The first is migration. Programmers can debug programs across multiple platforms seamlessly. For example, it's between an FPGA board and QEMU. The second is re-execution. Programmers can re-execute the execution state of software when a bug occurred for debugging. In the following slide, I will show you a use case of NEMIANA to explain these functions. In this use case, when a programmer runs the receive job function on the FPGA board, they found that stack memory has been corrupted, and they can find a buffer underrun vulnerability which is caused by Q value of -1. They try to seek the reason why Q has been set to -1. The programmer thinks that debugging on QEMU is easier to debug this bug. They send some command to NEMIANA, and NEMIANA migrates the execution state from FPGA board to QEMU for debugging with GDB. Next, the programmer wants to know what value is returned from the read number function. Basically, the return value of the function should always be positive according to the function specification. They operate NEMIANA, and NEMIANA moves 100 steps back before buffer underrun occurs. This means that NEMIANA reproduces the execution states, go back 100 steps, and re-execute the program on QEMU. The programmer steps into the read number function and observes how the function returns -1 by attaching with GDB. Finally, the programmer can find an integer overflow ban in the read number function. One of our major contributions is that we propose a migration mechanism with an abstraction model of CPU execution states and transitions. I would like to emphasize that the execution state of software can be migrated at any execution point developers try to debug. In addition, this migration can be done between different debugging platforms such as FPGA board and QEMU. We open sourced NEMIANA at this URL. If you want to use it, please get the source from URL mentioned in this paper. The key idea of NEMIANA is to design an abstraction model of execution state that does not depend on instruction set of architecture. There are two abstraction models in NEMIANA. The first model is model of execution state. The ES represents the value of CPU registers and memory at given step T. The second model is model of execution transition. The execution state transition represents the difference in the execution state since the previous execution state. Next, I will explain these two models in more detail. A processor in IoT devices mainly contains the following three elements. The first is CPU core that executes instructions. It includes a decoder unit, a calculation unit. These units does not have any execution states. And the CPU core has registers. There are general purpose registers, the program counter, and control registers. These registers determine the state of CPU. Next, the processor has memory that are written by CPU core via memory bus. For example, RAM, mass ROM, and flash memory are connected to memory bus. The last is peripherals that are written via memory bus like memory. Most processors have I2C, UART, timer, and CAN controllers. A set of registers and memory value determines the execution state of the processor. When a processor executes an instruction, the execution state is updated. The difference between execution state is execution state transition. A transition is the set of register or the memory and its value only contains an updated value. An execution state transition is calculated from a trace of instruction as follows. Arithmetic instruction, for example, add R1, R2, R3, store a result to a register specified as destination, in this case, register 1, so the transition includes the register. Jump instructions, for example, jump to 20010100C, loads a destination address into the program counter. So the transition includes the program counter, so NEMIANA handled as one of register. Store instructions, for example, store word register 1, SP, store the value of source register 1, in this example, to memory bus indexed by the base register stack pointer in this example. The transition includes memory bus indexed by the value of the base register. Load instructions, for example, load word register 1, SP, load a value at the memory bus addressed specified by the source register, in this example, stack pointer, to destination register 1, in this example, The transition includes not only registers but also memory bus indexed by the value of base register. The value of memory bus shows the volatile state of memory or peripherals. An execution state at step T is represented like this. RT denotes a set of value of register at step T, and MT denotes a set of value of memory in step T. The execution state is updated when an instruction is executed. In this example, the instruction is loaded immediate R17 0x10, and the value of register 17 is changed from 0 to 0x10. In this example, the execution state transition is denoted like this. This figure shows the architecture of NEMIANA. In the upper left box, it is the processor running the program to debug. For example, ZCU104. NEMIANA Bridge Client 1 collects the platform-specific trace information from Bridge Server 1 in the source platform. Bridge Client 1 then generates an execution state transition in common format and passes it to the state transition processor. The state transition processor stores the execution state transition in the transition DB and restores the current CPU execution state in real time. The kernel monitors the current execution state, processes system calls, and emulates peripheral devices as necessary. When a developer requests that a state transition at the step T be migrated to destination platform, NEMIANA restores the execution state at the specified step T. NEMIANA Bridge Client 2 writes the execution state to the processor via Bridge Server 2 in a platform-specific manner. The programmer can also use the debugging extension that uses the restored execution state, as shown in the lower left box. For example, a GDB can be connected to NEMIANA to check the program's behavior, or a module can be used to monitor buffer underrun. We implemented a plot time system for NEMIANA. The plot time system provides 3 debugging platforms using RISC-V RV32i as ISA. RISC-V is an open source CPU core. Next, we show the implemented platform to show how to obtain and write trace on each processor. Here are the debugging platforms. ZCU104 is a Xilinx FPGA board embedding a RISC-V processor written by Verilog language. This processor is modified for tracing instructions and migration. QEMU is a software emulator using the GDB protocol for tracing instruction and migration. Hi-5 Division B is a single-board computer that provides a data interface module for tracing instruction and migration. This slide describes a case study using implemented NEMIANA. Here are 3 programs used for this case study. One is DebugMe, a small original program for testing, and Drystone is a famous benchmark program. The last one is Core, a program from CTF security contest. Core contained buffer underrun vulnerabilities. We used each sample program in the case study for following purpose. DebugMe was for checking migration integrity of NEMIANA. Drystone was for measuring system performance overhead caused by NEMIANA. Core was checking if NEMIANA helped developers detect a buffer underrun vulnerability. We tested integrity of migration by migrating from one platform to another platform, and migration was also done from a platform to the same platform. We performed 3 tests on the destination platform. This table shows the result of the test. The leftmost column shows the purpose of the 3 tests, and the remaining column corresponds to result of each platform. All 3 tests were passed for all platform combinations. We tested the integrity by checking the status before and after migration using GDB. First, we ran Debugging for 500 steps on high-5 division B singleboard and observed the state of register at that time with GDB. The left side is a piece of the log output by GDB. This is the result of stopping at line 94 of Debugging and dumping the registers. That is the execution state at that time. Next, the log on the right was recorded when the execution state was migrated to QEMU and GDB was attached. We confirmed that the value of the registers at this time were the same as before the migration. Next, we used the Tristone benchmark program to measure the execution speed of program running on NEMIANA. When program was executed with NEMIANA, NEMIANA traces all execution instructions of the program. This trace generated system performance overhead and slowed down the execution. We measured how much performance overhead was caused with this benchmark. Without NEMIANA, this program took less than 1 second to complete the execution, so the time shown here would be approximately equivalent to overhead. The elapsed time differed between platforms. They were caused due to the difference of the way to trace instructions and transfer them to NEMIANA. The last case studies present an example of plugin for detecting vulnerabilities. The plugin in that we implemented checked if program accessed the memory region outside the previously defined segment. The plugin migrated an execution state of the program from ZCU 104 FPGA to a QEMU when a memory violation exception was detected. This case study demonstrates the following usage scenarios. First, programmer starts debugging a program on ZCU 104. When the plugin detects violation, it requests NEMIANA to migrate to QEMU. The programmer reruns the program on QEMU starting 10 steps before the violation occurs. This is a log when GDB was connected to QEMU after migration and debugging. Line 5 prints the value of the variable Q immediately after migration. On lines 7, 9, and 11, a single stepping execution was performed. The result of single stepping execution at line 11 shows that memory corruption had occurred and NEMIANA didn't receive any response from the QEMU. In this example, we want to back just 10 steps, but might be possible to further investigation the cause by going back to before the call to the read byte function and re-executing it. Finally, we conclude this presentation. We propose NEMIANA that support software development in multiple debugging platforms. NEMIANA provides a function to migrate execution state from a platform to another platform and executes the program seamlessly. NEMIANA provides the ability to re-execute and debug software at an arbitrary point in time. NEMIANA is open sourced for the research community to advance the further research of exploiting software vulnerabilities. As our future work, we plan to implement a debug tool that runs on the programmable logic of the FPGA board, leveraging an advantage of parallel processing that FPGA features. That's all I have to say in this presentation. Thank you very much for your attention.